Okay, thanks everyone for joining us for the Cinco Mayo edition of our quarterly meeting. We will have a couple of guests and stuff on this one, but I'll save those for a few minutes. The quarterly meeting, we will kind of highlight some of the things that we have done since the last meeting. This is a pretty long. We have a lot of stuff that's been going on, even though we're not having everyone report on this particular quarterly meeting. We still have a lot of accomplishments. So I do anticipate that we'll probably end up using the full 2 hours for this one. But if you are not presenting and you want to share something later, just let me know and we can send that out to the team. So let's go ahead and kind of get started. If you have any highlights you'd like to share, I'd like to kind of put those in. We did have a visit by Jim Bridenstine earlier this week and had the opportunity to talk about the ULI specifically. Is very excited to hear about that and still very involved and supportive in what's going on at NASA. But if you have anything else you'd like to share that we make sure we get out on either our Facebook page or one of the presentations, please let me know so I can include those in here as we do the quarterly meeting updates. We do have some in-person meetings coming up. The first of these is AUVSI. This is next week. So if you're going to be at AUVSI, please let me know. So that way we can coordinate a time that we can have the WINDMAP team meet up. I know we'll have quite a few people out there on at least the OSU side representing WINDMAP and the Oklahoma team members. But if I don't know that you're going to be out there, let me know and we'll set up a time. Likewise, we have AWA Aviation coming up. I know we have some papers represented. So this is going to be in San Diego in June this year. Paper deadlines for those of you that were on time were this last Wednesday. For the rest of us, we all have our extensions in place for deadlines due next week. If you have a WINDMAP related paper, however, the ULI team would like to know about that so that way they can coordinate an event at AIAA Aviation to let people know. So we'll likely have a meeting or at least a list that will go out with all the NASA ULI related papers at both AIAA Aviation and next year's SciTech. Stick on the meeting side here for a minute and talk about the proposed sessions coming up. So as promised, we do have some sessions coming up for both AMS and SciTech. So the AMS, we already have our topic proposals that are in. We're in the process of down selecting those. We will have a WINDMAP related session as part of AMS because I happen to know who's in charge of the ARAM meeting this year, and that is me. So we'll make sure that that does happen. So once that the session proposals have been finalized and we start accepting papers for those, I'll send that out to everyone so you know what to submit to. Likewise, Craig Woolsey is putting together a session for SciTech in Orlando next year for the Atmospheric Flight Mechanics program. So there'll be a special session on leveraging atmospheric flight mechanics for weather sensing at low altitudes. If you want to put a paper in, the process is a little bit different for SciTech since you have to submit a paper abstract to that. We can just send those directly to Craig by Monday, May 22nd with just a very short abstract with the information for the title and the authors for that particular paper. So I will follow up with an email on this for those that are interested in doing this one. And once the session abstracts are open for submission, I'll let everyone know about AMS. Okay. So any questions about any of these topics for this year?
Jamie, one other point. This is James.
Yeah, James, go ahead.
Yeah, so for the ISARA conference in Bergen, Norway, we are planning on having a workshop to support the WMO UAS demonstration campaign planning that might be relevant to some folks here on the call as well. And that'll be on Friday of that week. So
Excellent. Thanks. It's good to know. And Asara is still open for abstracts right now, I think through May the 15th.
That's right. Yep.
Okay. And I know we'll have a number of folks out here. If you end up deciding to go to Ursara, just let me know. So that way we'll know how many people we have from the WINDMAP team that are attending. Thank you, James.
Yep.
Any other inputs on upcoming conferences? Anything I've missed? All right, fantastic. Would like to do a quick set of introductions, and this is primarily for both the NASA folks that'll be seeing this after the fact, as well as some of our visitors today. We do have a couple of guests. Kind of a reminder of our team members, our academic institutions, in-car, and our industry partners that we have on the team. And these are our old faces, which everyone is now very familiar with. And we do have a couple of new faces on here I would like to introduce real quick. So let's start off with Jen. Are you on?
I am on.
Thank you, Jen.
Yeah, I'm with NASA Langley. I have in the past, I've worked with Jamie and Sean Bailey when I was at the University of Montana. And I'm working now with Grady Koch, and he invited me to sit in on this meeting just to listen in on what's going on. So thank you.
No, thank you. I appreciate you joining in. So happy to have you, Jen. I was really excited to see her when we visited Langley a couple weeks ago. And that should have actually been in my update list, listed to go out and give a talk there at Grady's invitation. Next up is Jay Shears from WindShape. Hey, you're muted, Jay. Hey, Jay. Can you hear us? There you go. Thank you.
Everyone, sorry about that. Yeah, and thank you, Jamie, for the invitation for WindShape. We have other people from WindShape on the call as well, and they can follow my introduction. I'll make my introduction very quick. I'm Vice President of Business Development located here in the United States, and looking forward to meeting you all.
Great. And I can't see my list right now, but I assume we might have a Guillaume on.
I don't think Guillaume is on, but myself, Nicolas Boisson. Hello, I'm the
Oh, hey,
CEO
Nicolas.
of WindShape. Thank you so much for having us in this meeting. Very briefly, at WindShape, we develop indoor drone test facilities. We recreate wind and weather conditions. So anything that's related to measuring outdoors condition to exactly know what drones will have to face later on is super interesting to us. So we are very happy to take part to this joint venture. Thank you very much.
Great. Thank you. Appreciate it. And I think there'll be some exciting opportunities with WindShape in the future, particularly when it comes to calibration and validation, as well as all-weather wind testing. They're doing some great stuff. Okay. Is there anyone else that I've missed that's joined as a guest today?
I believe we have Flavio Noca as well.
Flavio. Yes, please.
Yes. Hi, Jamie. Flavio Noca, I'm just a research advisor for WindShape, professor in Switzerland for fluid mechanics. And again, very happy to be here and hear about this very nice project. Thank you, Jamie.
Thank you, Flavio. Is there anyone else I've missed today? All right, fantastic. And I will not be going through, we do typically do a kind of a summary of the project just due to the amount of material that we have today. I'm going to skip that, but for those that have joined in today, I'll not only share these slides with you, but also our annual meeting slides that we presented back in January of this year that has a lot more information, particularly on the project goals, as well as more detail about all the various facets of the project. So let's go ahead and just get started then with our order of operations for today. We're going to do things a little bit in reverse since we've usually put the industry folks at the back. So thank you, Jay, for jumping in at the front and talking a little bit about WindShape. So we're going to start off with our industry partners first today with Crately and Apoorva, and then we'll jump into the three pieces that are represented today from observations, predictions, and implementation. So without further ado, I'll go ahead and jump straight to you, Crately.
Okay, very good. And Jamie, do you have my slides or should I share my
I
slides?
do. I have them here. So
Okay.
you're ready to go.
All right. Excellent. So just a very few quick updates. So Vigilant Aerospace is a commercial partner in the NASA ULI WINDMAP project. We provide airspace management systems with the core of that being a detect and avoid system that's based on 2 NASA patents that we've licensed. And so we've built that out into a system with an airspace display, integration to radar, integration to ADS-B in, integration to telemetry from multiple autopilots and flight controllers of various kinds, so that we can provide both standalone, in the field, completely disconnected, ground-based or onboard DAA systems that are industry technical standards compliant, or we can provide fully ground-based and UTM integrated airspace coordination and detect and avoid as a core function and feature. So that's real quick background on what we do. So we are participating in NASA ULI WINDMAP in order to be an implementation partner to begin to take the wind and weather hazard areas that are modeled, predicted, measured, modeled, and predicted, and turn those into avoidance areas in a fielded overall airspace management system. So that's our role here. And as a part of that, we are supporting the partners in this project to do field testing and flight testing. We have a particular goal, which I'll talk about in a later slide, kind of what those detail. One of our big announcements for this quarterly meeting is that the company was awarded an Oklahoma Center for the Advancement of Science and Technology sponsored research contract with Oklahoma State University and Jamie's team. This has some support also from the EDA through a grant that was made in the state of Oklahoma. And we're really excited about this. This is an opportunity for the company to advance its software to meet some important goals that'll support a variety of projects, including this project. So we're developing a fully networked multi-radar version of Flight Horizon. This is our product and our brand name. We integrate with a variety of radars now. There's lots of great work to be done around correlation of targets across multiple radars, so we can cover very large areas and long corridors, and have multiple radars feeding a single centralized system that is then providing all that information via UTM. So we're adding a USS user interface for our system. We already have a built-in UTM server for a local or regional UTM capability, a lot of additional sensor integration, and then we, under this project, will be doing extensive flight testing and field testing and hopefully corridor development with OSU. So very excited about that. Jamie, you want to jump to my next slide here? So I have a couple of slides here where I have highlighted some new features that have been added since the last time we did an update to this group. I've done extensive presentations in the past about the capabilities of our software and what we do, but these are some new things that you probably will not have seen. 3 things that are highlighted in this slide on the upper left here. We have built in the capability to have multiple sensors feeding into the system. We're still working on how to coordinate all those sensors and doing some of the correlation, which is what some of the contract I just described will support. But we do have extensive integration capabilities now, and are increasingly making those very sophisticated. So that's a new feature. We've also added the ability to add all kinds of waypoints and mission planning in the system so that you can do your planning and mission planner, upload that, track it, follow it, and use it as a part of your overall flight plan in Flight Horizon. And then this is a model here on the bottom left of us using a couple of different radars. This is in simulation only, where we would be doing either tracking live FAA data in a particular circumference area around an aircraft, where we're using live FAA data, or where we begin to have multiple radars that are tracking from different locations. So we've got one radar in the simulation set up near Stillwater, another one set up near Tulsa. Jamie, you want to jump to my next slide? So a couple of other features that we've added since I last briefed this group. We have added the FAA's obstacle database so that you can look at ground-based obstacles in your flights. We've had a lot of call for this and demand for this, and so we've added that now, just a couple of screenshots of that. And then as we are beginning to develop the full USS to support UTM interface for our system, we have these reserved area drawing tools so that you can begin to make your flight reservations in the UTM system. So that's an example of one of those. Jamie, you want to jump to my next slide? So some of our goals for this are to develop ConOps for beyond visual line of sight waivers. This is an important collaboration that we're very happy to work with any of the partners in this project on. We do have some upcoming plans with USRI, now OAIR, at OSU to do some of that here in Oklahoma in the 2023 and early 2024 time range. And we're very excited about that. These would be flights at high altitude into clouds, similar types of beyond visual line of sight flights. And then I'll say we have another couple of contracts, a couple of military contracts that we should be able to announce by the next quarterly meeting, in which our detect and avoid system is an important component of those contracts. And then we have some AAM contracts as well that on a longer timeline we'll be able to announce. So our system is being rolled out extensively and used by operators who have a mix of kind of medium to large UAS, including air taxi style aircraft and larger military drones, for example. So we'll be able to announce all of that hopefully by the next quarterly meeting. I think that's everything.
Yeah, thanks, Crately. Great stuff. Do we have any questions for Crately and his team?
Yeah, this is James. I just was curious what the last bullet said, because looks like the icon there got
There's a logo over it.
a logo over it.
Sorry,
Yeah.
I probably did that. I was probably copying and pasting.
Does it say something about data assimilation though? That's why I was curious.
Here, let me open another copy.
Sorry.
Here we go.
Thank you.
Yeah, so it's mostly about waiver and flight support and data collection using an active radar and tracking. And we do remote ID tracking as well, which is going to become really important in September. I'm sure you all are probably aware of that if you're flying drones. So all of those sorts of things.
To Crately, if anyone is interested in trying to implement some of this, what do you suggest is the best approach in terms of starting communication with you?
Yeah, absolutely. So, I mean, the first thing to do is to email me and talk about what type of flight testing you might be interested in doing, and then talk about the logistics of that. That's really where we start with this. And that's what we've been doing with OSU, of course, with multiple teams at OSU, is to work on the logistics of making this happen. We do basically have a field kit, and we do field testing. There are some photos from some of our field testing with OSU. And we do that routinely, and that's a great way to progress both what we're doing to test it, to demonstrate it, and then to provide essentially a ConOp and a safety case ultimately for your flight tests, particularly flight tests into clouds, which are going to be really important, and then other types of beyond visual line of sight flight. So just contacting me is step one.
Fantastic, thank you. Do we have any other questions for Crately? All right, great. I am very excited to see that you're working with Acme for some of the first deliveries.
Yes.
The nation's leading drone delivery service for things such as bird feed, shot, and anvils, I hear.
Yes, and TNT. Yeah. Yeah.
Don't tell the FAA about the latter one.
No. Yep.
All right. Thanks, Greatly. Very excited.
Greatly, will you be at AUVSI?
I will. Yes.
Okay.
Yeah.
Great.
And I'm speaking as well. I'm doing one of the solutions theater. So I'll be on the main floor and you can come see me make a presentation.
But what day and time is that, Greatly?
Oh, gosh, I should
I'll put you on the spot.
Yeah. I'll have to I'll post it in the chat here in just a minute. I have it on my other calendar.
Fantastic. Thanks. All right. Next up is Apoorva with a brief climate vision update.
Okay, great. Thanks, Jamie. So for those of you that are new, we're talking about the other radar involved in BVLOS flights, and that's weather radar. So our company is focused on basically low altitude weather observations, specifically when it comes to radar observations. And we realize the importance of being able to look at the weather close to the ground, 100 to 1,000 feet, where these drones will be flying. So we are rolling out a network of over 200 X-band dual polarization weather radars throughout the country, in support of not just drones, but also public safety projects, severe weather, flooding, tornado tracking. So that's the quick high-level summary of what the company does and why we are involved in WINDMAP. In terms of the quick update, we have 11 radars installed to date. You can see on that map over there, the purple circles are all of the radars that we're deploying in the southeast US. Each of them has a 60-mile radius. The yellow stars within those circles represent locations where we've already put a radar in the ground. So we've got 3 in North Carolina now, 2 in Georgia, 2 in Tennessee, 1 in Louisiana, 2 in Texas. And as you can see on the right-hand side, we've actually installed our first radar in Oklahoma. So additional radars will be coming in the coming months, and watch for more announcements related to that. On the bottom left, I just wanted to quickly show one of the quick advantages in terms of what having these X-band radars can do. On the left-hand side is a storm, moving through North Carolina as seen by the nearest National Weather Service radar. And then on the right-hand side, you can see that same storm visualized with much higher resolution with our radars. And this helps then, to start figuring out where the most severe parts of the storm are, but more relevant to drone operations, also being able to figure out exactly what the rain rates are, because some vehicles will have thresholds under which they can fly. So that's the capability we're hoping to bring as a next step here. And going ahead, I think similar to what, Cradley described, we want to be able to get the data from these radars into a UTM or, other location, other software, so that you can do exactly what Cradley is talking about in terms of identifying the weather hazard areas and then routing around it. So waiting for an opportunity to start integrating some of this data into the software that's being used. The last part I'll say is we are still not actively doing any sort of research project with any of the WINDMAP team members, but all of our data is available. So, we had spoken to Gus and others about maybe starting some sort of a project there, eager to get that going. So if there's any questions for me, I'll take them now.
Yeah, thanks, Apoorva. That's really helpful. Do you have a timeline for some of the other radar installations?
Yeah, if you let me know which sites, I can post those in the chat as I look them up. But generally speaking, I think of the sites of interest here, There will be one more radar coming up in Oklahoma pretty soon. I think this is still one of those three that's close to the Panhandle. We're still not finalized on a site around the Tulsa region. We're still in conversations, but let me go back and look and post in the chat if I know more of how close we are to that install.
Sure.
If there are other locations that people have questions on, I can talk about those and look those up as well.
I think in particular for those that might be doing some, Oklahoma and Texas Panhandle storm observations, there might be, some good ways to compare what we're getting with the UAVs with your radars. And so I think that would be helpful. I'll be real interested, particularly for the ones on the eastern side that overlap with the test ranges in Oklahoma, because obviously that would be benefit with the regular flights that we're doing as well.
Yeah, there's one radar that's on the overlap between Texas and Oklahoma, and I can tell you that'll be up in by the fall.
Fantastic.
Yeah.
Any other questions for Apoorva?
So if we want to use this in this high resolution data in real time use, what sort of bandwidth and data rate would we need to access that?
I guess it's just a function of the use case here specifically, right? And what sort of data that you need. Do you just need images from us? Do you need the actual raw data files? So I think we'll have to go down that path to narrow down what you need. But the data will be coming out at least every 3 or 4 minutes, but we will have lower scan data coming out every minute as well. So it can be as much as, a throughput, like every minute imagery of, an entire scan.
Thank you. That helps. I'm specifically thinking of, what would we need if we were trying to work with this on board a drone or in a field operation. So thanks. That helps.
I think the most useful way to integrate all of this information, especially from these radars, would be kind of the way Vigilant is doing it, right? Where the data goes into a UTM type system, it gets processed there, and to the users, it just shows up as, risk polygons or hazard polygons saying, do not fly in this area.
This is Adam from UNL. I'm wondering if you have explored visualization of these data in some of the more common platforms, some common software like the Gibson Ridge software or the Weather Climate Toolkit, Hawkeye.
We're working with a bunch of those. We've already done visualization in Gibson Ridge as well. And we've seen some of the images there, and Gibson Ridge helps with like the 3D profile. And that's really helpful.
Do you have that set up for real time?
It's a kind of a case by case as someone comes and says, well, this is a piece of software we're using, we can get the data in.
Yeah, I'd be curious to test this out in real time this spring for the Oklahoma site using the Gibson Ridge software. Is it something that you can distribute in real time, or is it something that has to be analyzed after the fact?
No, this can be done in real time. So, I think we're talking about a project here. If we can set that project up, we can have the data go into Gibson Ridge in real time for display.
Okay, I'll touch base with you offline. Thanks.
Thanks.
Great. Thanks, Apoorva. Appreciate that. If anyone has any other questions, please reach out to Apoorva directly. All right, and then we'll shift now to our observation track, and we'll start off with Sean.
Thanks, Jamie. So we are looking, our general objective is investigations of surface atmosphere interactions. So we're kind of approaching that in 3 fronts. One of them I'll be talking about, and that's where we're looking at trying to quantify representativeness or uncertainty in order to assimilate the UAS data into numerical weather predictions. So we're talking with NCAR on kind of how to potentially implement and test data assimilation. We also have Garrison, who will be talking about some of the work he's been doing looking at how to improve our ability to measure vertical fluxes using multi-rotor aircraft. And Anissa will finish up with a couple quick slides talking about some of the work we've been doing, looking at ways we can measure droplet size using hot wire probes. And this is part of what we're trying to do with this is see if we can contribute to the planned OSU measurements in clouds to see if we can add or see if we can participate in some way and help out with those measurements. So I'm just going to start off, and I've talked a bit about this before. So this is last summer we did a series of measurements where we were trying to look at the influence of terrain on the variability of measurements. So we did a whole series of measurements where we looked at we conducted coordinated flights over rough terrain near the Kentucky River, and also as more flatter terrain at our flying field. So we did this with VTOL flights, which made it a lot easier to operate in kind of the rougher area where we wouldn't have had a runway to land the fixed wing. But the idea is to get this sort of distributed measurements over a large grid space. So next slide, please, Jamie. And the way we've been analyzing the data is trying to get an estimate of how much uncertainty is associated with if you have a numerical grid cell and a particular numerical time step, and then you're assimilating a single UAS that is somewhere within that grid cell, making a measurement somewhere within that time step. What's the uncertainty associated with that particular measurement that's not really related to the aircraft itself or the sensors itself, but more related to how the terrain might be altering the wind field and the transport within that wind field. So we took the data from those measurements, we crunched them, looking at the variability within different time and space bins, and that's what we're seeing on the left. So this is just one of numerous flights we've looked at. And this is the wind, and we're trying to estimate the 95% confidence of the wind measurement based off of wind, assuming averaging over up to 500 meters versus time steps up to 1500 seconds. And what you're seeing there is a visualization of the uncertainty associated with that variability. So the way to view it is we're seeing up to 40% uncertainty if we take the largest area and time step that we're looking at. This is for wind. It was much lower for temperature and humidity, but that also the percentage is based off of the absolute value of the quantity we're measuring. So what we've done is we've looked at those distributions and realized that they can be modeled using some simple turbulence models. And what is on the right is taking the turbulence parameters of turbulent kinetic energy, dissipation rate, and integral length scale. And with that information, we can estimate how much variability we can expect to see in a certain range of time and space distances. And that's what we're seeing on the right is what the model predicts the uncertainty to be. We're still underestimating it a little bit, but it's still getting good agreement. So we've been in just this week. I talked with James and Young at NCAR, and then we're trying to figure out how we can kind of coordinate with what they're doing there to see if we can kind of merge our two approaches and test it with some flights. Next slide, please. So Garrison's going to talk about some of the work he's been doing at modeling the flow field around UAS in order to help us get these sort of vertical flux measurements.
All right. So, hey, everyone. My name is Garrison. And like Dr. Bailey said, my portion of the study is focusing on flux measurements from multi-rotor UASs. So currently, we're using CFD to identify locations that are free from the influence of rotor wash. Below is an example of a craft that we can analyze in our study to place measuring devices like the sonic anemometer shown below. So our main goals are to examine the influence of cross flows and how that'll affect rotor wash generation just for optimal sensor placing. The image on the right is actually a model of the UAS depicted that we plan to use on in our study. We've been testing both transient and steady state cases so that we can strike a balance between accurate solutions and minimal computational costs. Just so we can apply this method to several vehicles rather quickly, but also reliably. The main parameters being considered here are rotor wash, which equates to thrust, the rotor diameter and rotor count, and the various wind or crosswind velocities that the UAS might encounter. Next slide, please. So currently we're investigating the appropriate boundary conditions that will give us reasonable results for a single rotor. This is being done for both transient and steady state cases, so we can make sure the results are comparable and reasonable. The two GIFs below show the velocity magnitude and streamlines of two steady state rotors with opposite directionality of the fan condition. And we can see both of those exhibit actuator disk behavior. The image at the top right shows a slice of the velocity along the YZ plane for a steady state rotor that was similar to the first two, but with an expanded domain just to test for the boundary effects that can occur in these studies. And finally, the image on the bottom right depicts the velocity streamlines for a transient case. We see that these mainly take effect at the rotor due to that no slip condition on the face of the rotor. And so our next steps in these projects are to finalize both of these models and implement it on the full UAS configuration that was shown on the previous slide. So thank you. I'll turn it back to Dr. Bailey.
Yep, next slide, please. So Anissa will talk about some of the work we've been doing, estimating droplet size using hot wires and the OPC and free particle counter.
Hello, everyone. So the objective was to develop some methodologies to measure the cloud or fog water droplet sizes, and we're hoping to be able to contribute to the OSU's campaign. So there are three methods used here. One is using a laser-based particle sizer, OPCN3. The other one is we use the hot wire. And then we have some published data that we're going to compare these two to that. So on the bottom left, the OPC is shown, and then so we put the hot wire on the aircraft, and it's placed downstream of a wind tunnel. We are trying to use the flight speed, measure the droplets at flight speed. And the mist maker is also placed there, and the mist maker just creates, it's a ultrasonic mist maker with monodispersed mists or water droplets. And so on the top right, you can see the voltages, and then on the bottom right, you can see the normalized droplets. This is just for one small window. Next slide, please. And here we can see that the distributions for the hot wire, the particle sizer, and the published data, they actually match pretty good. So some of the next steps that we are thinking of to investigate various sources of droplet sizes. And that's it. And hopefully to get some in-flight data to test these techniques and see how they work.
Thanks, Nisa. Yeah, we actually have some I guess this is that's an old slide. We can ignore that one. Oh, and that one. Oh, I sent you all my old slides. Sorry, Jamie. You can skip through that one too. Yeah, that one. Yeah. And probably that one. There we go. So these are all our updates from last meeting. But anyway,
that's probably not your fault. That's probably my fault, Sean. So I'll put us back.
I wouldn't put it past myself at all. Yeah, so I guess that's where we actually have flown with the OPCN3 and did on a foggy day, and we were looking for something else. We were trying to track a plume, but everything got washed out because we were on the kind of the foggy day. We were actually picking up. I think we were picking up the fog particulates. So that was accidental, but confidence boosting for those types of measurements.
Great, thank you, Sean and team. I appreciate that. Do we have any questions for the UK team?
Sean, I have a quick question for the last speaker. I'm just curious how long of an averaging time is needed to get to calculate the distribution. Is it 10 seconds of data or 1 second or something else?
Sorry, was that question for me? It's well, it's 1 second.
Okay, that's pretty instantaneous. Okay.
Yeah, we're sampling with the hot wire. We're sampling 20 to 200,000 times a second to resolve those spikes.
Mm-hmm.
So we are picking up every droplet that hits the hot wire, and so what we're measuring is the moisture that hits the hot wire as it vaporizes. It leaves that transient spike. So the hot wire itself, I think, is several hundred degrees Celsius. So the vaporization happens quite rapidly. So we're able to pick up pretty dense droplets.
This is a great comparison.
Yeah, I'm pretty happy with it.
So if you're able to do a profile, does it keep drying off and then moistening up again, so you can kind of get data points as you go up?
Yeah, absolutely. Yeah, so we can. So the couple of the benefits of the hot wire, the big benefit for me for the hot wire is that we can actually get simultaneous turbulence parameters with it, so we can kind of filter out the spikes and get what's left should be the environment conditions. So as you could fly along, we'll be able to pick up what droplets we're hitting, what size they are, and then kind of what the turbulent environment is where we're flying. So we could absolutely do profiles and get these sort of distributions as spatial variables.
Oh, that's great. Thanks.
And one question. Sorry, my headphones, the batteries in my headphones died. So I have a question for Dr. Bailey. In your quantification effort, you showed a graph where I think my understanding is the error variation with respect to time and with respect to space in a topography during a flight over some rough topography, right? The question I have is, what kind of error analysis or error assessment did you use, like in terms of equation, or if it's not a direct equation, did you use any sort of filter that gives you some sort of error analysis? Is that, in other words, I'm asking the background of
Yeah, so this is really just the variance, right? So it's the variance in the wind field.
Got it.
And the motivation is that we want to use this in a common filter, right? As the uncertainty. And there's going to be, we're boiling it down to two error sources. One's going to be the sensor error, which could be quantified by the manufacturer or the data provider. But there's going to be another source error that's going to be associated with just, you'd have one measurement within this 500 meter box in this 500 second time step. That is only going to represent, if you imagine a Gaussian distribution, 1 point somewhere in that distribution. So that what we're looking at here is assuming this is looking at the breadth of that Gaussian distribution we'd expect to see for a certain or for different sizes of domain.
Got it.
A very small domain is going to have, in a very short time, is going to have a small distribution. So that's why the error drops down low. And then the bigger the distribution, the bigger the space, the bigger the time step, the broader that distribution is going to be. So the error is bigger associated.
And did you do any sort of interpolation between data points you've collected, or because I would imagine you won't be able to get measurements at every point in this?
Yeah, no, we're flying with fixed wings and we're measuring roughly 50 times a second. So we're getting resolution.
Got it. Oh, I see. Okay.
Or so.
I see. Okay. Thank you. That answers my question. Appreciate it.
Great. Thanks again. Let's move on to our next speaker, McConan. Timely.
All righty. Thank you very much. Good morning, everyone. So I'll be filling in for Dr. Woolsey, and I'll be presenting a couple of work that we've been working on in our lab here. But first, I guess to kind of summarize what our lab is working on, we have three. We're working towards wind velocity estimation, but we approach it in three different efforts. Right, we've spent a great deal of time trying to model the aerodynamic modeling and the aerodynamic force and moment modeling of our various platforms to establish some sort of model that we could use in some sort of model-based estimation scheme. And so we do a great deal of system identification of multi-rotors, fixed wing, and recently we've added a Dragon and eVTOL into our, fleet. And then if we're successful at identifying accurate models for these aircraft, then we incorporate these models into an estimation filter like a Kalman filter or an H-affinity filter or an extended Kalman filter to do wind estimation during flight, either in real-time processing, but for the most part, so far, we've been doing it in batch. We've also developed capabilities where we can have in situ wind velocity measurements through the use of anemometers or air data units that allow us to reconstruct wind and compare these reconstructed wind to our estimated wind that we've gotten from our filters as means of comparison. So far, we have a fixed wing in our fleet that is operational. The picture that I'm showing you here on the left is that fixed wing. We lost that plane. We've replaced it since. And then we have multi-rotors, which we call the hexacopter, which is currently being equipped with an anemometer to allow us for that in situ wind velocity measurements. And then we've recently added the Dragon into our fleet. And we plan on equipping that with 2 air data units. That allows us to get 2 separate wind velocities throughout our flights. Next slide, please, Jamie. All right, so one of the efforts that we've been working on so far is essentially we spent a great deal of time trying to identify an accurate model for our fixed wing. And the argument that we pose there is most of our flights are done in turbulent air. And so the point of having a steady model for these aircraft was no longer valid, right? So we needed a better model. The effort that we spent is whether or not we can include unsteady aerodynamic modeling or unsteady aerodynamic parameters within our aerodynamic models to allow us to capture wind velocities, the mean wind velocity, but also the fluctuations of these wind velocities. And so I think in the previous meeting, Dr. Woolsey presented that we've been able to do that. We've developed an unsteady aerodynamic model. We've established methods that allow us to capture these parameters and identify them quite accurately, and then use those unsteady aerodynamic model into a Kalman filter setting to allow us to not only to estimate the mean wind, but also to see if whether or not the unsteady aerodynamic model does indeed capture wind fluctuations in addition to the mean. And so what I'm showing you here on the slides is there are 2 graphs. The one on the left you see are wind velocity estimates that are developed or that we got from an unsteady aerodynamic model-based Kalman filter, and the other one from a quasi-steady, which is commonly used in literature. In other words, the unsteady effects are ignored. The quasi-steady models are shown in yellow. the unsteady model-based wind estimates are shown in red, and the blue line is what we consider our truth that we've reconstructed from air data units. And we're comparing how the red and blue compare to the blue, but also how the red compared to the red. And so right off the bat, one thing that you can see is that the red is more sensitive to fluctuations. Because it's the red and yellow don't exactly match with the blue, then one way to compare whether or not if these fluctuations are indeed wind fluctuations we're capturing and not necessarily fluctuations due to estimator tuning, we compare the energy content, which is shown on the right here. And what you could see is that almost exclusively, and we've done these plots for multiple flights, is that the red and the blue match in terms of energy content, which kind of leads us to believe that we are indeed capturing fluctuations that the quasi-steady simply doesn't. And so the punchline here is that an unsteady aerodynamic model allows not only to capture the mean velocity, but also the fluctuations in the Kalman filter setting. And these works are shown in the bottom publications, which have not appeared yet. The first one is the modeling and unsteady aerodynamic process that's summarized in a journal paper that has been submitted. And the other one is where I show these plots, and that is the basically the estimation process that includes unsteady aerodynamic modeling, which we plan on submitting very soon. We've also been working on a survey for wind estimation methods. Any questions so far? If not, next slide, please, Doctor. Okay, thank you. And the other effort that we've spent in our lab is one aspect of the work is focusing on the model of the aircraft themselves and if they improve the wind estimates. And the other is the filters themselves. What can we do to the filter to allow us to capture wind velocities more accurately? And in this work, we developed an H-infinity filter where essentially we've how do I say, we haven't made any sort of assumptions that a Kalman filter generally makes. We've eliminated that. And the goal here is to see whether or not that H-infinity filter that assumes basically zero assumptions on how the wind behaves or most of the assumptions that a Kalman filter requires does better than the Kalman filter. And what we're showing here is, yes, it's true. It turns out that an H-infinity filter performs better than a Kalman filter, or I assume in other types of filters as well, in that context, right? And it's less restricting because you don't have to make assumptions. Any questions here? If not, next slide. Oh yeah, and this work was presented at SciTech last time, and they're turning it into a journal paper. And the other work that we did, which is consistent with what I explained so far, is now instead of using a fixed wing, can we develop a model for a multi-rotor that works on a large domain and not necessarily around the small linear regime? Can we devise such experiments, or can we devise such models for a multi-rotor? And can we use that model to do wind estimation again? And the answer is yes. In this work, Jeremy is developing this work, and these two works have been presented, I believe, at the Southeast Control Conference and the Virginia Space Grant Consortium work, where Jeremy at least showed that he is able to iteratively develop a model that works on a larger domain so that these multi-rotors can be used in very turbulent air and actually estimate wind velocities that wouldn't be able to estimate otherwise. And remember, this is not direct measurements. These are model-based estimates. And that'll be it as far as our efforts so far and our updates. And next slide. Yeah, and as far as the lab updates, we have a couple of students that won the Virginia Space Grant Consortium fellowships. And Jeremy, I believe, went and presented the work that I mentioned earlier at the Virginia Space Grant Consortium as well. And Dr. Woolsey is now serving as the AIW Atmospheric Flight Mechanics Technical Committee Chair. I think that starts on May 1st. And we have various flight test plans devised for the summer or planned for the summer. We seek to calibrate our hexacopters, basically the anemometer we have that we've implemented on our hexacopter. So if anyone has done it previously and they have some wisdom to share with us, please do so. We've developed a bunch of air data units. Since we lost our first one, we learned that we need a bunch in our fleet, and we'll be doing a bunch of wind tunnel characterization. And more importantly, we'll be doing a fixed wing, multi-rotor, and eVTOL system identification flights, but also wind estimation flights. And with that, I'll finalize my update.
Great. Thanks, McConan. Fantastic stuff. Do we have any questions for McConan and the Virginia Tech team?
Okay, thank you very much.
All right, thank you. And moving on to Imran.
McConan, that was really cool to see. I've got 5 slides here, so if you'll just get us started. So just a review of kind of where we are. We're looking at multi-agent wind field structure estimation. Some of these techniques will also be applicable to mapping out clouds as we start to fly in them. But we're starting with this sort of idealization, this AZZ-Zuckerwaard-Zardeman model of a rotating flow. That's sort of our surrogate for a flow structure. It's originally intended to replicate a tornado, so it has basically size, speed, and location, and those are the structural parameters that we were really interested in. And so in previous work, we set up a wind inference algorithm. Wasn't H infinity, but it did return an estimate of the local wind conditions. That was Ujval's work. And then we started to look at basically chasing the maximum information contours. So every parameter estimate has, some error. It's position dependent, so it's time varying. And so now we started to get into how could multiple agents sort of systematically reduce the individual error. Jamie, would you change slides? And so just a little bit about what that formulation looks like. This is a little bit of work that's in progress just to be able to talk about it. This is an example of 4 connected agents, all nodes globally reachable as an approximation, and we're estimating the maximum velocity contour based on relative information weighting. So first off, we need a notion of individual information. How much is in each agent's information gathering? And so from Manzi's work, we've basically used this sort of data density, gradient variance, and gradient magnitude term. And this is grounded in Shannon information entropy. But it does have some additional terms that sort of recognize the digitization side of things. So if we just want to really just do a information weighted sort of average of those, we're effectively going to define this sort of weighted adjacency matrix. And if you look at the update rule, it looks sort of involved, but that's just because there's 4 agents. On the right-hand side, you'll see basically the new estimate is a sum through all of your agents from 1 through n of this sort of weighted information times that particular agent's estimate. So effectively, we're taking, we're trusting the highest information agent more strongly than the other ones, but we're allowing all of them to participate in the convergence. And so this is a sort of an intuitive construction, and we've previously simulated the behavior of this and sort of started to look at what the distribution of error was. And so we're now asking, especially in the case of a biased estimation, does this update rule guarantee the estimates converge to the true value? So that's one reason for formulating in this. And I'll just kind of, next slide, please, show you kind of where that goes. There's some manipulation, some massaging that I'll sort of spare you. Effectively, we can rewrite this into a recursive formula that looks like this form here. If I look at the form in the bottom left, right, it says our new estimate is a function of some matrix times our innovation error plus some other matrix times our initial condition or initial estimate. And so that's element-wise multiplication with that star there. So that's not, we've got matrix multiplication and element-wise multiplication. This is different than the sort of traditional multi-agent systems, which would guarantee convergence for just matrix multiplication times the innovation or effectively iterated powers in the initial condition. So this sort of intuitive construction that we built lies outside existing theory, and so we have some work to do to ensure that this will converge to the convex hull of the original of the estimates, because we're not just using a one-time information, we're using sort of this constantly updated information contour. If you go to the next slide. So we talked about maybe how might we validate this, and this is something we've been working with Jamie Jacob and Brian Nelbing on.
And so starting to look at some complex flow structures, and we have this sort of nice circulating whirlpool here at Oklahoma State University. And so our first idea was to say, let's look at basically putting some markers in that flow and starting to digitize them from an aerial view and running PIV on that. And it sounded like it'd be a fairly straightforward problem, but we ran into some fun things. Jamie, if you'll click on if you'll just click again, effectively what happens is all of the shade ball markers sort of collect together, right? And so they sort of attract each other. And in terms of what that actually looks like, if you'll click again.
Look closely at where the cereal meets the liquid.
There we go. This is sort of what was named the, just sort of first quantified in 2005 and named the cereal effect. And so effectively what's happening is those local bodies are causing this sort of minuscule rise here, and then floating objects will then sort of ride that contour and actually draw together. It's going to require a little bit of creativity to kind of get around that and ensure that we have sort of free-flowing objects that don't bunch together. So that's going to some of the summer 2023 planning. And then I think the last slide. So the last slide, and this is a project that isn't funded under this work, but we're looking at different funding opportunities for it. Just wanted to kind of highlight it. The idea is that, if we're entering into these sort of high wind conditions, potentially, rotating flows, we're going to be entering with UAS that have varying thrust ratios from passive flyers and balloons to, sort of very high thrust to weight ratios and gas turbine powered vehicles. So we're starting to ask this question of how come, a measurement UAS sort of balance both sort of riding along the wind field versus sort of actively powering through. And, as we find, these are the best places to make measurements. How do we start to, intelligently drive ourselves through that? So we've approached this with two different threads. One is a theoretical investigation, sort of setting up the energy balance, kinetic energy, potential energy that lets us get into this sort of Lagrangian and Hamiltonian dynamics formulation and look at when things are conserved, when quantities are conserved. And the second is to, directly code up a simulator, a wind field flight simulator, which we had from this project, and start to look at how we would integrate that. And so it required, modifying that a little bit, but we're now seeing examples of both entrainment and escape. And we have some theoretical results that say basically under what conditions you could sort of get entrained in this sort of vortical flow versus, when you would have the right conditions to sort of exit it and transit through it. And so that, I'm just showing you two different simulation examples in Patrick's work here, just in terms of, these may be, so for example, the measurements that you're going to get from the left, the entrainment versus the escape contour are significantly different in terms of what you'll actually pull out about the wind map or the structure under there. So I think that's all we had to highlight today.
Great, Imran. Fantastic stuff. Do we have any questions for Imran and his students? Okay, thank you very much. Appreciate it, Imran.
Thanks.
All right, moving on to Adam. We're about halfway through our slides and about halfway through our time, so we're actually tracking pretty good right now. That doesn't mean you can be a laconic, however, Adam. So,
yeah, I took that as an invitation to talk as long as I wanted. No, I'm going to go through this pretty quickly because just in the interest of time. But also, I'm going to be documenting some work that one of my PhD students has done, and so if you have more questions, I'm going to probably direct you to him. But first and foremost, Stephen, the one who led the machine learning models of DCI work, is successfully defended, and he'll graduate this May. So that's good news. As a perhaps reminder, but for those of you who haven't seen this before, we used a thunderstorm observation by radar. That's the Thor algorithm we developed a number of years ago to develop this climatology of thunderstorms. To over 11-year period, you can see the domain, Central United States. And I think Stephen's talked a little bit about the distribution and some of the work that he's done to cluster this using a variety of tools. But what I want to talk about a little bit today is some of the more recent work where he used random forest models to try to predict deep convection initiation. So DCI here is deep convection initiation. So you can advance the next slide. So one of the things that he wanted to test was whether it was better to have a single model trained on the entire region or models trained individually, that is on these subregions. And these were chosen pretty deliberately based on the distribution. We had one in the northern plains, one in the, we call the inner mountains, southern plains, and southeast. I won't go into details of why we chose those, but that was the gist of what he wanted to do. So next slide. And so kind of the takeaway here, sorry for the quality of these images, they're not all that great, but if you train a model based on the full domain, it does best than training models on the individual domains. And then so you can see a couple of visualizations here, the area under the rock curve, the rock is receiver operator characteristic. And essentially this is pretty good performance, not great, but pretty good. And there's not a lot of difference between the individual distributions. As long as they're off this dashed line, it means that they're decent. But the takeaway here is that, and then the next slide, Jamie, if you show that, the other thing here is if you test a model that is trained on the full domain and then test it on the individual domains, but train it on the full domain, it actually is still better, with the exception of the southeast. So this red dot here, this diamond is the model trained on the entire domain. So the bottom line here is that if you train it on the full domain, it tends to do best. And again, this is only the central part of the United States. That might change if you trained it off the entire CONUS, but at least gives us some insight moving forward. So next slide. The other thing that he wanted to evaluate is whether including spatial information actually improved the prediction, because the other ones didn't go into many details, but these are trained off the RUC/RAP model analysis data, and using a collection of parameters that we've determined in our own work and other folks' work to do pretty good at predicting deep convection initiation. But the one thing that was not included in those was spatial information. So when you include that, the prediction improves. So the purple triangle, sorry, purple diamond here is a little bit includes the spatial information, and the prediction is improved. And what's interesting here is that it's not actually learning differences in the parameters, the geographic differences of the parameters. It's actually learning the localized climatological patterns in DCI. And that's kind of getting into the weeds here, but I guess it's worth just throwing that out for completeness. And I won't go into too much detail on this far right figure, but this is false alarm, a probability detection, and CSI, but the predictions are okay. And there's a pretty high false alarm on this. There's a pretty decent probability detection. But so these models that he developed are good, but not great. Okay, next. And so I'd be happy to take questions on that other piece, but I'm going to just jump into something we're thinking about the next steps, and not necessarily the next steps with regard to Stephen's work and deep convection initiation, but just in general where we want to move with the funding from WINDMAP. And I wanted to float this idea, and I say this is a new research focus. This is a potential new research focus. It's something we've been discussing in my group, but also I'd like to expand the discussion to the rest of you guys as we think about field campaigns, perhaps taking advantage of the WMO DCI, DC demonstration campaign. But one of the things that we've identified in some of our work is that there is an indication of deep convection initiation being more favorable downstream of an urban heat island. And the way we did this, and I, again, won't dig too deep into this, but we used the same database. This is not Stephen's work. This is another student, but used the same database and then looked at the distribution of deep convection initiation points downstream of cities. And these are the cities that we used. So we clustered them into small cities, the blue ones, big cities, the red ones, and then coastal cities, the green ones, and generally ignored those coastal cities because there are other influences beyond the urban heat island, but we still looked at them. So next slide. And so one of the things we found, and I don't expect you to read the numbers, but the colors here indicate that in general, downstream of these big cities, particularly the big cities, there is a statistically significant increase in deep convection initiation. And so the yellow ones show that it's actually not more likely downstream, but in general, we see that the green boxes indicate a statistically significant higher likelihood of deep convection initiation. We broke it into a whole bunch of different categories: winter, spring, summer, etc. But the gist here is that it's a bit more likely to see deep convection initiation downstream. And when we compare that from upstream to downstream, you still see the same basic gist. But this is motivation for exploring this idea that these urban heat islands might be more likely or might create conditions that are more favorable for deep convection initiation. If you go to the next slide, so as far as why this is the case, people have looked at urban heat islands, but there's been limited, I won't say zero, but limited work on examining what in the vertical profile of the atmosphere is more supportive downstream. And there are a lot of hypotheses, but what I wanted to kind of latch onto here is some of the work that we did as part of the lapse rate campaign back in 2018. This is work that one of my students did, where he looked at all the flights that were conducted, synthesized them, and broke them into irrigated versus non-irrigated. And so essentially, the three plots here, the left is the vertical profile for non-irrigated red, irrigated green of potential temperature. And not surprisingly, it's warmer over the non-irrigated. And this is one snapshot at 17Z, but we see this across multiple times. And if we look at the middle one, not surprisingly, the irrigated has more water vapor in the water vapor mixing ratio in the lowest levels. What's interesting is that this is confined to a fairly low level, the lowest several hundred meters. Then above that, you kind of lose that signal. And when you put these together, what you see is that this quantity equivalent potential temperature, which is kind of the entropy of the air, and an indication of the potential energy of the atmosphere. We see that the signal of a more favorable, more energetic atmosphere for the irrigated is really confined to low levels. And so if you go to the next slide, one of the principal findings from this is that if you look at the typical metrics, typical parameters used to predict deep convection initiation, the pattern shifts depending on whether you focus only on the surface or you look at a deeper layer. So if you focus just on the surface and say, how does irrigated versus non-irrigated favor or impede deep convection initiation, it suggests the irrigated conditions, or rather irrigated atmosphere, is better. It's more moist, it's still pretty warm, and so the typical parameters are more favorable. However, that changes, that flips when you consider a deeper layer. And so, when you consider a deeper layer, the non-irrigated is more favorable in many ways. And so I want to try to combine these two ideas and to look at how the urban heat island impacts deep convection initiation, and not just at the surface, but looking at deeper levels, deeper layers. And so I think this does lend itself to a field campaign that flies UAS and doing profiling downstream, within, and then across, that is either upstream or on the cross flow of the urban heat island, and to see whether these parameters that we typically use to predict deep convection initiation are different, and for similar reasons. That is that the urban heat island certainly affects the atmosphere, increases the heat content, but also probably reduces the amount of moisture. But is that focused mainly in the low levels, or do you see a pattern, a signal deeper into the atmosphere? So I just want to float this idea, see if to get any feedback on it, but I also will try to take answer any questions regarding Stephen's work
Yeah, I mean, I have so many questions on this last piece. I think the first one being the impact on what our planned field campaigns are. I mean, how can we leverage some of this in terms of what we're proposing to do in some of the urban areas. That's probably it's a lot longer discussion rather than just probably a short question, but there's so much there that I think we can try to mine. But it does it. How much of a difference does it really make at the end of the day versus an urban heat island versus an irrigated heat island? I mean, I'm sure there are going to be lots of parameters that are going to be very different, but some that'll be similar.
Yeah. I mean, ostensibly, yeah. And then it's going to be different seasonally. It's going to be different based on the size of the heat island, the size of the city. So yeah, the parameter space is enormous, but there might be this project maybe that is WINDMAP might be an opportunity to start diving into some of these questions.
Yeah, and certainly I feel like going back to this, I mean, at what point do you think you're going to start to see the temperature crossover?
Yeah. I don't know. I mean, this result was surprising.
Yeah, I mean, I'm shocked that it's so consistent.
Yeah.
Okay. Any other questions for Adam? They can be answered in a minute. I think most of the questions we have are probably going to be like an hour-long discussion. I think this begs that we probably need to have a follow-up meeting to really delve into more of the physics of what we want to get out of some of the field campaigns.
Yeah,
probably sooner rather than later. Any questions or comments for Adam? All right, thanks, Adam, and thanks, Stephen, for us. All right, next up, is this going to be a James or Domingo?
Hi, everyone. It's going to be myself, James. Domingo was unable to make it, unfortunately, but would like to participate in planning field campaigns for this summer and how FastEddy could be used to help do that. So hi, everyone. So I'm going to give a brief update on progress at NCAR and some of our interactions with the University of Kentucky. Just to kind of step back, the goal of the work at NCAR is to develop methods for accurately simulating fine scales through a combination of data simulation, mesoscale to microscale coupling, using FastEddy and other LES models, and machine learning techniques. And I just list a few of the recent milestones here, and moving into year 3 where we are now. And one of those areas has been the work of Jin-Kyung Kei here at NCAR to estimate observation error variances, which are needed for the data simulation component. In the past, we had just used values that had been previously used for commercial aircraft. And now we're starting to take a crack at understanding what these error variances look like for UAS and looking at differences between fixed wing and multi-rotor UAS as well. And so hopefully we can kind of present an update on that next time. We've also recently adapted our ensemble data assimilation system to produce ensemble forecasts that we can use both for observing system experiments to assess the value of UAS and data denial type experiments, as well as to incorporate UAS observations in real time. So we're moving toward sort of a real-time end-to-end system where we could get data from UAS, process it, and assimilate that data into a data assimilation system based on the ensemble Kalman filters, which what we're using here. There's a few publications that are in progress and actually getting pretty close to submission, including one by Jeremy Sauer that's looking at an evaluation of FastEddy in complex terrain. Another one by Jin-Kyung Kei, who will describe the methodology that we implemented based on the EMTIS and REGI method to estimate the observation errors. And I think also we may incorporate some of the work that we're doing with University of Kentucky on this. And then finally, the paper that I've been working on here, funded primarily with another funding source, the FAA, but also somewhat leveraged up with funding from this project to do a simulation of University of Kentucky UAS observations for the improved prediction of fog at a local airport there in northern Kentucky. Some of the highlights from the data simulation side of things, on the upper right there, showing a comparison of data Denali experiments, so conventional observations assimilated on the left, and then the addition of UAS observations on the right. And this is a comparison of the relative humidity at 2 meters above ground level for an independent observation location at the airport. And so basically these are just surface measurements, which is challenging because the UAS is, obviously flying above the surface. And so we're seeing a positive impact though, which is really encouraging. You see reductions there in the bias, root mean squared error, and correlation is increased quite a bit for this particular case and location. And then on the bottom there, some of the results of our initial ensemble predictions. This is a 10-member ensemble, and we're comparing, again, conventional only data simulation with a simulation where we're including the UAS. And one of the things that we found interesting was that in this system, the spread of the ensemble isn't really changing all that much. And it's very hard to tease out even the impact of the simulation of UAS using this ensemble approach. However, we're finding more recently that if we use the ensemble mean, 40-member ensemble mean, we are seeing some positive impacts, which I'll show in the next slide. And then on the right there, lower left, talking about some in progress areas, working on additional case studies for fog prediction, finalizing the evaluation fast eddy. And then I think that we talked about this in the previous discussion with Adam, is sort of the 2023 testbed planning, and hoping that we can talk about this sooner than later. So maybe we can use that as an action item here to sort of plan our next planning meeting here in the next few weeks. Next slide. So this is just another comparison of the impact of UAS data simulation on the model analyses that we're generating. On the top panels, I'm comparing data collected with the UK Hover 1 profiling aircraft. You see it's flying up to 120 meters. The dots are actually the model values at discrete points in the vertical and in time. And then the color contour fill is from the UAS. And so one of the couple of things you can kind of see is the variability in the impact of the data simulation, comparing the control run on the left with UAS observations on the right. One area that jumps out is earlier in the simulation period, the observations are indicating it's quite a bit colder than the model is indicating. And you see these biases are being corrected somewhat well when UAS observations are assimilated. And then another area which is important for fog prediction is here later in the period between 3 and 5 local time near the surface. You see the control run has sort of a dry bias. The relative humidities are tending to be closer to 90%, whereas with the UAS assimilated values, you're seeing that the values are jumping up over to 95, closer to 95, 96%. And then when you just look at this in a different way with scatter plots, you can see the impact quite clearly. Again, the bias is better, root mean squared error for relative humidity is better, and the correlation goes up quite a bit. And this is again for the profiling site, which is located near the airport. Next slide. So this is sort of the overall result that we're seeing. This is one of the simulations we did. Again, conventional observations alone versus conventional plus UAS. This was one of the cases where we had pretty significant fog, as indicated by satellite in the cyan colors within the Ohio River, which is basically the border of Kentucky and Ohio and Indiana. You can also see some areas where there's fog extending into Kentucky along the river, other river valleys.
Then I highlight two areas, one with the black circle and one with the red circle. And so if we look at the black circle first, we'll see that's sort of centered on the asterisk, which is where CVG Airport is. And they reported some fog in the early morning hours. And so one of the difference that is we see, this is the probability of relative humidity exceeding 99%, so essentially indicating fog. And so if you look back and forth between these two plots, the center and the right, you see that the probability has increased in the vicinity of the airport quite a bit in the simulation with UAS. And you can also see some really interesting features that, these are really fine scale features, but you can see an area of increased likelihood of relative humidity exceeding 99% right within the river valley and the panel on the right, which you don't see with conventional only. So this is a really encouraging result. We only had 2 profiling sites and we're still seeing a positive benefit both locally. And then when you look downstream over Ohio, this is an area where there is the purple color is indicating a very high likelihood of relative humidity exceeding 99%, in other words, fog. But the fog product from satellite shows there's nothing really going on there. And the impact of the data simulation is showing that it's reducing these probabilities. So again, having a positive influence on the forecast. So these are very encouraging results, and we continue to process other cases to see if this is consistent across other cases. Next slide. I'm going to transition here now to Fast Eddy. I've briefed this before, but just to kind of give you the background of the case area that we've been looking at. We've been simulating high resolution simulations of urban impacts on flows for 2 cities predominantly at this point. One of them is Oklahoma City, and the other, which I'm showing here, is Dallas-Fort Worth area. And we employed the mesoscale to microscale coupling. You see we start off with a very large domain. This is sort of you're capturing the synoptic scale. And then you window in on the area that you're interested in using essentially WRF to get down to fairly fine scales, down to 3 kilometers or even 1 kilometer resolution. So you can really resolve the mesoscale. And then we use that to drive Fast Eddy. And there's a number of different key advances that were done over the past few years to be able to do this in an efficient way. One of them is called the cell perturbation method, which essentially allows you to rapidly spin up turbulent eddies on the edges of the domain. So you don't need as large of a domain to get accurate representation of the smaller, very fine scale atmospheric motions. The other thing that Fast Eddy allows us to do, because it's a GPU-based model, you can run multiple cases. And so on the lower left there, we see a set of 31 or 30 different days where we ran Fast Eddy with different inputs from the WRF model, basically showing the day-to-day variability. And one of the things that jumps out at you is that you can't really use a typical day by just using an average profile, because every day is so different. And the impacts locally on both sort of the strong flows through urban canyons and associated turbulence really vary depending on what the upstream stability and wind shear profile looks like. So it's a complex interaction that you really have to be worried about. And so we're going to focus in on a case in the next slide that looks at a very dynamic case in which a frontal boundary passes through the Dallas-Fort Worth area. And Jamie, if you could click on the lower left panel, it's a movie loop of the evolution of the wind as the front passes through this domain. And so you start off with this sort of lighter winds from the southwest, and you can see that the brighter colors are stronger winds sort of making their way through the different urban canyons. And now, as the day goes on, the winds are shifting, and you'll see here soon that a frontal boundary passes through, resulting in a very strong shift in the winds. And now you see that here comes right now the shift in the wind direction, and now they're much more intense through the domain. And so we could do that for each of these different domains. You can see the little squares, maybe clicking on one more, you can see different building morphologies are going to result in different flows through the urban canyons. And yeah, so they're all going now. So it's a very complicated high rate. So one thing to point out here is that each of these boxes is essentially one grid cell in a model. Maybe two, but actually these are 9 by 9 kilometers. So in a typical HER run, you're talking about 3 by 3 grid boxes that cannot possibly resolve these fine scale details. So if we go to the next slide. So what does that mean if we sort of look at this from a, see if it's going to advance here for us. Yeah, so we've done some comparisons with the available observations within the urban canopy, but they're few and far between. But essentially what we end up seeing is that the variability, for example, in the winds as given by this black curve is very significant on the order of plus or minus 8 meters per second, depending on where you are in the urban canopy. Now, if you go to the next slide, we can quantify this and compare it to what you get if you just use the mesoscale model. And so here we break it down into prefrontal, during the frontal passage, and post-frontal, what the distribution of low-level winds look like throughout the domain. And so you can see that prefrontal, the model actually isn't doing too bad. It's the WRF model, sorry, is not doing too bad in comparison with fast eddy. But once you get a more dynamic situation passing through the domain, you see that the WRF model really has trouble handling the variability of winds across the domain. And these winds, especially on the tail end of these distributions, would be highly impactful to, for sure, small UAS operations, but also UAM in general. And if you go to the next slide, we see a similar pattern in the vertical motions, which again are going to impact urban air mobility in terms of ride comfort. You can imagine during frontal passage and afterward, you're going to have the fast eddy model indicates the ride is going to be quite a bit more bumpy than you would get from just using your typical output from the operational models. So I think that's all I had here. Let's see if there's another slide or not.
Nope, so. That's it.
That's it.
Okay, James. Thank you very much. Do we have any questions for James and the NCAR team?
So just want to say that we would like to coordinate or collaborate in sort of using fast eddy potentially as a way to plan an urban-based field campaign to try to understand, where you might want to deploy UAS or what types of winds you might expect on a given typical day. Like we could pick 4 or 5 different configurations of winds coming in from different angles and different stabilities, and then look at maps like this to see, where it might be interesting to set up UAS profiling sites, both with flux measurements or just even measuring the mean winds that come through the domain.
Yeah, I think it's a great idea, James, and that again necessitates an additional follow-on meeting, really to focus on what we're going to be doing on the field campaigns.
Yeah, that sounds good.
Hey, James, I got a question about the fog DA. I mean, we still saw something similar with Matt's work assimilating UAS data, other data, and that is that the forecast was just really bad. And there's really nothing, it didn't seem like there's anything we could do. Well, I mean, we improved it a bit with the assimilation of some of the targeted data. But what do you think needs to be done? And I don't mean at the model level, but in terms of perhaps DA or observations to improve those fog forecasts?
Yeah, it's a good point. Fog is a challenging forecast, especially because it can be such a localized event. That's the types of conditions we were trying to predict. I think some of the larger scale forced fog events, aren't quite as unpredictable as these. But one of the things that we want to do is sort of look at the impact of varying profiling strategies, which you could do with observing system simulation experiments. This was more of just a pilot study to say, hey, could we demonstrate a capability where we could work with the Weather Service, decide whether or not we were going to fly, so more of the targeted campaign. and with limited resources. Only 2 UAS were available. Obviously, I think you'd want to have more than that, but we don't know how many more that we need to actually make a more significant impact on the predictions. So I think that's where this needs to go. And I know you're also thinking along those lines to do observing system simulation experiments. There's pros and cons to that because you have to assume that you're able to actually replicate a sort of a true environment. And for these types of simulations, the Ohio River is only 700 meters wide, or maybe a kilometer wide in that area. So you need to your nature run has to have very high resolution. We're talking 100-meter probably resolution. So it starts to get really expensive to do those types of simulations.
Yeah.
And I think that the similar thing could be done for the heat island type studies too, which would be interesting to see if you could replicate urban heat island with a nature run. And then for cases where you're interested in the convection initiation downstream, and then see if you can actually duplicate that, or improve on those types of predictions with UAS observations.
Yeah, I know urban heat island does show up even in the HER, even at 3 kilometers. I've seen that in at DFW.
Mm-hmm.
That doesn't mean you're doing it correctly, but it's certainly there. But yeah, no, it's a good point.
I was going to say too that we actually saw urban heat island effect reducing fog at the airport that we were trying to predict fog for. Turns out that CVG airport with the red asterisk there is less likely to have fog now than it was 30 years ago because of urban heat island effects.
Interesting.
And we see that influence in the model too. We see a drying because it's warmer. It just tends to have lower heat relative humidities.
Yep.
All right, thank you, James. Appreciate that.
Yep. Thank you.
Okay, Nicholas will be talking about implementation today from Nicoletta Falls Group.
Yes, hello everyone. I'm filling in for Dr. Fowler today, and sorry if there's background noise. They just started some construction, so sorry for that. So just to put it back on what we were doing, we were working on the implementation and the integration in the national airspace. And in the past, we identified the stakeholder and their needs, and now we are venturing in this bottom branch on this figure. So basically, we are developing strategies for using the UAS for data collection and evaluate the impact of those strategies on the national aerospace through the simulation. Next slide, please. So right now we are looking into 2 different ways to collect the data, and that is open for further strategies on the go. But for now, we're looking into a spiral and more local data collection just as a proof of concept, and that's highlighted in this map, just to visualize how that would look. And we're trying to evaluate the impact using an agent-based modeling strategy, and we're using the following agent for that: the airplanes filling the airspace and the weather data collection UAV following this collection path that's mapped out here. The data we use to model the aircraft is real traffic data, which we collected from crowdsourced ADS-B through the Open Skies network. I show something about that on the next slide. And then we would basically want to evaluate the impact of the collection strategy based on the outcome, which could be no influence, a detection and avoidance by the aircraft, or a collision with the drone. And for that, we would just vary the positioning, the strategies, and the amount of drones to just have some different parameters in the study. So far, we have sourced all the data and we have set up the simulation framework in Python. And over the summer, the plan is to conduct the full simulation. Next slide, please. So just to give an overview over the data collection itself, we defined the data collection area, which I also will detail later, then queried the OpenSky database. We did some process on the data, like just filtering some outliers and filling in missing data if possible, or clear some data. And lastly, we analyzed and extracted some information. Next slide, please. Okay, and there you can see some of the results. We have 3 areas which we sourced. We tried to look into areas that are different, have a different representability of different scenarios. So we picked Reno, North Central Oklahoma, so the area shown on the map to the left, and the state of Indiana. We collected data over 20 days, and overall we sourced 17,036 flights at different altitudes. Like, for example, for Indiana, we went for the full airspace up until flight level 180, while for Oklahoma and Reno, we only viewed smaller portions and lower altitude airspace. On the left, you can see a heat map basically of military aircraft in Oklahoma, which is a result from the data collection. And you can see that there's clear movement patterns in the airspace, although only shown 2-dimensional. And this already can be used as an indicator of where to place or not to place drones for data collection. Next slide, please. Now the next step with the data we collected would be to just use the raw flight data for simulation, like use a list-based simulation approach, or we just use deterministically the flight and propagate it based on the list. However, if that is not possible, we have also sourced some probability distributions based on the flight data, and that could be used then to do a Monte Carlo approach and drawing like parameters from these distributions to run a Monte Carlo simulation. And one of these distributions is seen on the left with the ground speed for jet aircraft in the data set, and we could just use the best fitted distribution, and we have those for all parameters in different types of aircraft. Next slide, please. And that's lastly about the airspaces we were looking at. Just to give that some, like where we looked at different altitudes, we tried to look in airspace like Indiana, where there's lots of en route traffic, so general aviation, military, and civil aviation, and with ideally fixed traffic patterns and fixed spacing and more higher altitude, to see if there's any influence on this type of operations. The Reno area fulfills the purpose of looking into a terminal operations area, so an area that's close to one or multiple airports, sees lots of traffic that follow certain rules, but overall can be more random. Like, for example, in Reno, we have lots of scenic flights, which sometimes take random patterns, and therefore we're only looking at lower altitudes. And kind of the same is true for northern Oklahoma, which basically should be where we want to look at the influence on mostly VFR traffic, and there's generally no regular traffic patterns. And for that, we would look at low and medium altitude. And I think you could see that very good at the military traffic patterns, that there's some areas where there's military training, and outside of this, there's basically no clear scheme seen. That's why we want to look at all of those different airspaces to just evaluate the influence of the UAV operations in those, and if there are different takeaways for placement of the UAV. Yeah, that's the update from our side. And
Nicholas, this is a little bit of an aside, but I think we can utilize this to help do some of our flight campaign planning, because one of the issues that we always have, obviously, is getting the approvals for either the waivers or the COAs. And part of that requires us to do a risk assessment, which is very dependent upon the population as well as the density of the air traffic within the area. So I think we should discuss that and include this in kind of our further analysis as we move forward with the flight campaign discussion for the summer.
Yes, definitely. I think probably then from the areas we're looking at, like something like northern Oklahoma would be most interesting, I guess. So we could also try to, once we have the framework set up, it should be easy to extend that for other areas too.
Well, and I'd also like to kind of include some of what Apoorva was talking about earlier with the location of some of the radars Because I think in particular, if we start to overlap where they have radar coverage, that'll provide us the capability to, combine our assets.
Yes, that's.
Do we have any other questions for Nicholas and the Nicoletta's team?
Jamie, you just said a lot of the things I was going to say. This is really interesting work, what you're doing. And I think Vigilant would be very interested in having a further discussion with you about some of what you're doing. And Jamie, I'd love it if you were involved in that further discussion as well. So I'll just leave it at that.
Yeah, sounds good. I think there are things we can leverage there greatly. So let's spend some time talking about that next week. And then I know Nicoletta will be coming back soon. So we'll get Nicholas and Nicoletta involved in a discussion once she returns to the States.
That sounds great.
That's good. Yeah, I also noted that, so I can pass it on to Dr. Fowler.
Fantastic. Thank you very much. All right, our final presentation of the day is going to be a bit of a team tag event. We had a group that went out to Boulder for the Marshall site observations. And so I'll just go ahead and turn it over to whoever's going to start discussing that.
I'll get us
all right, Gus
started.
Jumps in.
Yes, but before I do, to actually do a proper segue from the previous presentation, it would actually be beneficial if Nicholas, you could list this location, the NCAR Marshall Field site, because it has so many good instruments, as one of the areas of study, because we are working with a very close by airport to do the in-cloud measurements there. So knowing those kinds of information would really help the waiver process there.
Yeah, I think that and the ARM site would be two really ideal sites for us to do some further analysis on. Right.
Yes. And I'm worried that we might have an older version of the slides here, but we'll see what happens.
I think we're good. That was left over from the last time. So
okay, there we go.
Yes.
There we go. So on the 14th, we went to Marshall Field, which is an NCAR facility, to test two systems and the wind measurements and also the behavior of the systems in winter weather conditions, right? Because as we talk about having year-round operations of UAS and UAM, these vehicles will have to encounter these conditions and either know how to avoid them or how to withstand them. So we went to test some new instruments that we were developing to measure these kinds of environments and what are their impacts on the aircraft. So I'm working more on the instrumentation and the development package, as well as Braden on the wind measurement side of it, and Alyssa is doing all the really neat science of the actual impact on the aircraft and how that hinders flight and flight operations. And so if you can go to the next one, Jamie, please. So we had two main systems that we were testing. One was our precipitation sampling system that has temperature, relative humidity, an optical particle counter, and a millimeter wave phase array radar on it. And we were testing Braden's system that he's going to talk about it a little bit later, where he is working on a servo gimbal that compensates the movements of the UAS to keep a sonic anemometer always well oriented with the ground for measurements of 2D and 3D wind speeds, along with UV and W components. The Marshall site, it's a great place to test because not only it has several instruments, but also offers a variety of weather conditions. And in terms of air traffic management, it's also very interesting because you have a lot of traffic from the Denver National Airport, a lot of regional, smaller traffic through Rocky Mountain Airport that's within 5 miles of the location we're flying. And at the same time, the Rocky Mountain folks are really willing to collaborate with us for us to fly within their airspace and do these in-cloud measurements there, which we're still working on the waiver for. If we can go to the next one. So in this one day, we had a enormous variety of conditions, which was really interesting. And for me, particularly coming from boundary layer measurements and kind of pre-storm environment measurements and even CO2 measurements, I had a few other field campaigns that were winter weather related. And it was very interesting to see how how different the operations are in this kind of environment, and also how way more demanding on the systems they are. And we had several failures that were interesting as learning opportunities on how we need to change and adapt these sensors for these kinds of environments that I'll talk about. So we had, if you want to go for the next one. We had various conditions, and this slide here shows a picture of Alyssa, Braden, and I at 2 p.m. local time, where we had just some fog and some drizzle, and then by 6 we were fully white out, and then by 7 it was like it never had snowed on the ground. And so the conditions were changing really fast, and it was a really interesting case. I'm sorry, James, but I took great pleasure in seeing the forecast fail miserably, because that's the whole reason why we're doing what we're doing, right? We want to improve the forecast conditions based on UAS measurements. And so it was really interesting to see how the conditions changed very quickly. And even if we were an operator trying to plan a flight, let's say a beyond line of sight flight, and we're trying to use the weather forecast to plan our flight and be safe around the weather conditions, we would have failed miserably. So this was a very interesting case. Go to the next one. And so we saw all types of precipitation, all sizes of precipitation, and we're still looking at the data. This was 2 weeks ago, a little bit more than 2 weeks ago, and we're still we're gathering data from NCAR and then our data from all our systems and sanitizing data. So what you're going to see here today are some quick snaps of the raw data and what is it looking like and what story is it telling us. If you want to go to the next one. And so I think Braden can hop in here and talk about his research and his measurements with the sonic anemometer.
Yeah, so my name is Braden Rivard. I'm a grad student under Dr. Jacob, and I work with experimental validation and testing of UAS-based wind measurements and wind sensors. And so we took one of our house-built quads that we had built at Excelsior out to the Marshall Field with a Trisonic ultrasonic anemometer, which takes wind measurements at 5 hertz and gets UNV components along with a vertical wind components as well, up to about 60 degrees. But we did a 10-meter hover test between the 2 towers. Each tower has wind sensors at 2 meters, 3 meters, and 10 meters. But unfortunately, one of the towers was inactive on this day. So we were only able to do a comparison with one of the wind towers. You can go to the next slide. And you can see here, this is just a full day of the wind. You can see there's the 3-meter and the 10-meter tower in orange and gray, and then our UAS sensor in blue. This is just the full day. I have a zoomed in view on the next slide. You can go to the next slide. And as you can see here, here's the flight measurements that we got. You can see on the left is the ground test, which was just the sensor pretty much just sitting on the ground, getting the wind speeds at about half a meter or so off the ground. And then on the right is the 10-meter hover test. As you can see, I apologize, I didn't pick the best colors for this plot. But during the 10-meter hover test, our UAS sensor matches very closely for the first 2 minutes to the 3-meter tower, and then very closely for the next 3 minutes of the hover to the 10-meter tower. It is a bit different. We were probably about 30 or 40 meters away, so it would potentially be a little bit different of wind speeds, but the results were very encouraging, I would say. You can go to the next slide. And so for some next steps, we actually have 2 UAS mounted wind sensors. One is a Trisonica Mini, and the other one, which we've previously talked about, is our sensor with the Trisonica Sphere. We'd like to do further tower tests back home as well. Be able to do we have our own mast sensor, which we have. It's a Young 81,000, that also is an ultrasonic anemometer that we mount on top of a 10-meter tower, where we can take comparison measurements between those and also some Oklahoma Mesonet tower comparison flights, which are very similar to the towers that we flew next to at the Marshall Fields. And then once we fully experimentally validate that these sensors are taking accurate comparable wind measurements, we'd like to do some wind mapping around the Kerr-Drummond dormitories on Oklahoma State University campus, which are abandoned, and would be able to do some really cool wind mapping, just pretty much just experiments and techniques. So you can go to the next slide.
And so on the precipitation side of things, this is a general view of the conditions of the day, right, that we're measuring. And the bars on the temperature, humidity, and wind speed plots here are showing when we did 4 of our vertical profiles to 400 feet, where we were testing the precipitation sampling system. We can go to the next one.
Yep.
Okay, and so looking at the optical particle counter measurements, it was very interesting to see different behavior from the ground to the top of the profile, which is 120 meters, about 400 feet, right? That we can clearly note that not only we had larger particles aloft, but we had larger counts of these particles aloft than we were actually receiving on the ground. So in this case, if you're trying to do a flight planning based on a ground station, an ASOS kind of deal, that you're saying like, oh, these are conditions, my UAS should be fine because I'm so close to the ground. This low altitude flight shows that even within 100 meters off the ground, you're seeing very different conditions that could lead to icing and other problems in flight. If we can go to the next one. And these measurements of temperature, humidity, made a mark there with errors. So take them with a grain of salt, because we had a failure on one of our systems on the aspiration of the sensors. So the only aspiration happening in these sensors here is based on the smaller fan of the OPC and the general mixing caused by the multi-rotor blades. And so since we also had issues with keeping the UAS outside for long periods of time and having the autopilot be too cold to start, we had to start taking the aircraft inside to kind of de-ice between flights. And so there could be some warm bias from going from inside to outside. We tried to leave the sensors out a little bit before taking off, but so take these with a grain of salt. But the interesting part here is that the design of the relative humidity measurements that protects the sensors from direct exposure to the precipitation, but still allows the moist air to go in through a two-layer system air intake did show that our relative humidity measurements were lower and more detailed with height than the tower measurements, because the tower measurements at this time were just pretty much saturated and not showing anything really that was happening in the environment. And the temperature measurements agreed with the tower, and even though they're not aspirated to the desired airflow rates, they still showed an interesting variation with altitude. That if we go to the next slide, we're going to look at that with the it's one forward. It's the one that has the OPC and the temperature. Yeah, there we go. We see that for mission 1, where we go from cold to warmer back to colder. We see the distinction of particle sizes between the ground and aloft, because of this slightly warmer region. Could be because of this slightly warmer region. I can't say it right now because the measurements, like I said, are not ideal. And then on the final mission, where we had a more constant temperature profile, we don't see that distinction as well between the particles seen closer to the ground and the particles seen aloft. So I thought that even though we had several system failures that you only learn about when you go out and measure things and redesign systems so that they're more resilient, I thought it was very interesting to see that even with the failures, the agreement is still there between the sensors. I thought it was interesting initial partial results to share. And later I'll process the data from the onboard radar, and those will probably be shared with the community on the Friends and Partners with Aviation Weather meeting coming up in 2 weeks. That's what we had for our updates.
Yes, this is Apurva. I have a question.
Go ahead, Apurva.
I was just wondering, in terms of all these validations that you're doing, plus when you think of operational needs for weather information, specifically for rain, what do you think, what's your assessment so far of the value of radar-derived rainfall information? I'm sorry if I missed that in your presentation.
No, it's very good, and you and I have talked about it offline a lot about this. I think it's very important, and I was really happy to see on your presentation that the Oklahoma site is going, and so I'm going to start gearing up to talk to you and do some co-located studies there, because the interesting part of doing this study at Marshall is that Marshall has the regular, let's say the normal coverage for the national airspace, which is the NAX-RED and terminal Doppler radars, which you know really well that doesn't show a good picture of precipitation below 3,000 feet, right? In particular, the really small precipitation, like the drizzle, freezing drizzle. And so I think from what I've seen, the drizzle, freezing drizzle is a more imminent threat because it is harder to detect from radar because of where the reflectivities lie, and also because it has a immediate risk for propeller icing, control surface icing, or general aircraft. But rain, if it's heavy enough, right, would certainly affect flight of underpowered, in particular if you have any effect of soaking of the aircraft, changing the aircraft weight, that would definitely impact flight conditions. But I would say Alyssa is probably a better person to answer this question, or Farouk also would probably be a good person to answer this question. But I imagine a heavy downpour would be a severe risk. And like I said, the smaller drizzle, freezing drizzle kind of events would be also kind of a hidden risk.
Yeah, I would say it just really depends on your platform and what you're worried about. There are so many different things that, whether you're waterproof or icing proof or, what you're really looking for. There are a lot of unknowns when it comes to danger and precipitation in general, or lack thereof danger.
Thanks, Apoorva, Gus, and Braden. Do we have any other questions for the Marshall Field Campaign team? And I think overall, for those interested in utilizing the Marshall site, James is the best point of contact right now for that. I anticipate there'll be some future opportunities for joint Marshall visits.
Yes, highly recommend. Great team over there. Scotland, Darcy, Jacobson, everyone really nice. Their infrastructure is nice too.
Yeah, it was unfortunate we didn't have the EOL tower there, which goes up to 30 meters, but hopefully we could have that in place at some point if we coordinate it with the different parties interested here.
Do you have any other any trips planned out there yet, or?
Yes, I'm actually redesigning a couple of things on the system, and if there is any precipitation event or low clouds, things like that, I would definitely be interested. And since it's close by, it is the kind of location where we could go based on forecast, because within a day we can drive there with the systems. So yeah, I can give you a heads up.
Thanks. It's exciting stuff.
Gus, are you bringing your system out for AUVSI?
I saw actually your message on the chat. I am not attending AUVSI.
Oh, you're not? Okay.
But
Yeah.
we could still bring your system out. So you just have to.
You can fly it up in Marshall. Yeah, do a demo up there.
Yeah, the system it with everything UAS, right? Whenever it is under development, usually it has its quirks.
I know.
So I don't know if it's reliable to say like, here, just turn it on and use it. Usually it takes me a year or two to get it to a system like that. It's like, yeah, take it out of the box, turn it on, and use it. It's gonna be perfect.
Understood.
Right. Yeah. Right now it's still pretty much a low TRL prototype where I'm understanding the behavior, the sensors, how they're working together, how they're affecting the aircraft to begin with, even placement and things like that. But I'll talk to you and we'll figure something out.
Okay, we'll keep an eye on the weather too for you.
Great.
Yes.
Yeah, and just kind of as a follow-up to that, so we were talking about taking some of the systems out to AUVSI for the Oklahoma booth, but we decided that either they were too low TRL and still a little too janky to show on the booth, or they were too operationally far along and we don't want to take them out of their field measurements for a week and risk getting them damaged during transit to AUVSI. So Braden will be relieved to hear that we decided not to take his system away from him, so that way he can keep taking measurements and finish his thesis. But I should mention, and thanks for reminding me about this, James. For those going out to AUVSI, there is the collocated event on Monday with the in-car weather forum. And we did present there last year, basically a summary of what WINDMAP is doing. But it's a great event to go to for those that'll be out there. It's a free event.
That's right.
You have to sign up beforehand.
You do have to sign up, but it is free registration. I mean, it's part of your AUVSI registration.
Correct.
And I would just point out that this year the focus is on using UAS to support emergent environmental conditions, so wildfires, heavy snow events, other hurricane resiliency, and so forth. So sort of a different focus than we've had in the past.
Yeah, it should be very good. All right, so we are at the noon mark, and so I think we'll finish up with one final slide. The Choctaw Nation team couldn't be here today, so we just wanted to give a quick update on where they're at. They have now gotten approval to do several BV loss flights, and so this is full no VO BV loss flights up to about 6 miles in distance right now. So they're currently pushing the envelopes on altitude with a goal of 5,000 feet AGL, and so they're hoping to accomplish that this summer. So that way we can be doing in-cloud flights in the fall at the Choctaw Nation site. So I'll keep everyone posted as that kind of marches along. I don't think that's going to have much of an impact on our current summer flight campaign discussion, but we will look for options for that as we move forward. Do we have any other folks that want to jump in and talk about what plans they have for summer flight campaigns?
Hey, Jamie, I'll jump in real quick and kind of we're new to this community. We maybe just do a quick update on WindShape and what we're doing in Tulsa. I don't need any slides if that's okay.
Yeah, sure, that's fine. Thanks, Jay.
Yeah, okay, appreciate it. Well, hi everyone, and it's really great to meet this community. And boy, a lot of relevant activities. I think where WindShape can add some value. I think for this quick update, because we're kind of new to the community and collaboration, I think I'd like to just do a quick introduction of WindShape and what our latest initiative is in Tulsa, Oklahoma. Basically, we were founded back in 2016 to fill this void in the field, really, of experimental aerodynamics, and happy to have a couple of the co-founders on the call with us, Nicholas Basson and also Flavia Noca. And our goal really was to fill this void in experimental aerodynamics by commercializing this new family of wind generating equipment that we call the WindShaper. I think that the specific void that we're addressing is that I think we all know on the call today, testing commercial drone today is really challenging because there's really no good repeatable environment that exists to reproduce the real operational flight conditions that you're all talking about today, and be able to capture that data, mitigate it, quantify it, and validate that data. So today, most recently, we come out with an announcement, and happy to say that we are moving a solution, maybe to the problem, here to Tulsa. We're going to be located over at the Skyway 36 facility, over behind the Osage Casino, with a 19,000 square foot facility to try to fill this void. We're going to be opening a wind and microweather, calling it a microweather testing, inspection, certification, and validation facility here in Tulsa. It's going to consist of 8 indoor laboratories in one location. It'll include a propulsion lab, a climate lab, high-speed lab, wet lab, subsystems lab, EMC lab, and here's the exciting part, 2 free flight activity labs that'll use our proprietary WindShaper technology, really intended to reproduce the actual flight conditions so that you can test the drones indoors in a repeatable environment, make sure that they're safe to fly in the tram corridor and also in the National Airspace System. So currently, we're in pre-construction mode. We've signed a lease. We're looking to open up the facility and be operational, maybe in 8 months from now. And the facility, as I mentioned, is located over at the drone port here in Tulsa. And we really plan to localize the capabilities to be relevant and meet the testing, inspection, certification, validation needs really that the industry has right now, with reliable data capture for operators, regulatory agencies, and manufacturers, and also this initiative as well. So, just quickly, it'd be great to we'll follow on in other sessions with more details about some of the great work that our team's doing. But certainly, we can open up before that time with some discovery discussions, scope out some of your projects, and look at how we can replicate it and realize it in this indoor environment. And kind of help you with, the repeatability, capturing the data, mitigating it, and validating your data in this environment. So we're really excited to be here. And thank you, Jamie, for inviting us to this session. A lot of really, really, really great stuff. So hope that helps.
Yeah, thank you, Jay, for that. I was just throwing up here real quick. Let me go back to sharing again. If anyone has any questions for Jay, I was going to show up a quick slide. We've been really impressed with the technology that they're going to introduce here and that they've been developing over a number of years. And we think it has a lot of utility for our problems here. So I think it will be a natural fit for many of the things that we'll be doing here in the future.
So I had a quick question.
Sure, go ahead.
Do you do anything with regard to icing situations, in particular, like snowfall? Because at NCAR we have a snow machine that we've developed that could be of value possibly to you if you don't already have that.
We do. We can also provide you with kind of a white paper on how we do it. But hey, I'd like to open up the response to this to the other WinShape founders on the call, including Flavio and Nicholas, to kind of add some explanation to this to give you some more detail on how we do it. Flavio or Nicholas, would you like to jump in? And
yes, sure. Thank you. As Jay mentioned, yes, we did some icing condition testing before. The way we did it is that we set up one of our machine in a climate chamber, in a cold chamber, where we had control on the temperature, and we did not play with snow for the icing condition, but we did inject some very small water droplets that were then freezing on the propellers. We have a white paper on that. It was just a proof of concept, something we are looking to develop further, and that we'd be super happy to discuss further with you. We currently don't have any snow machines, so that's other type of tests that we've been doing as well, also in cold chamber, not to study icing, but just to study drones in snowy condition. And do you have ways to recreate artificial snow any time of the year? You do? Really cool.
Yes.
So
yes.
Maybe we can connect and set up another call to chat about that further.
Well, and James is going to be at AUVSI next week, so there'll be some opportunities there as well.
Right. Yeah, we could discuss it there, and also I could bring in our colleague that developed the system to talk more about it. They've been working really hard to sort of have it represent actual snow concentrations as closely as possible in terms of size distributions and water content, and that they can closely monitor, so they can say, what was the snow rate, what was the distribution of sizes, and then they're focused more on the de-icing aspect of things, but this could be relevant for sort of in-flight too. It'd be interesting to combine it with the wind tunnel in some way.
Yes, definitely. Let's keep in touch and schedule a meeting next week at the UBSI, if that's okay.
Okay, yeah, sounds good.
I'll loop everyone in on via email on my side, and then we can find a time.
Please, yes, I would very much be interested in that.
You too, Gus. Okay.
Yeah. Then the other immediate question is, how soon can we start designing experiments and scheduling experiments to do with you guys?
Well, their first tunnel is being shipped right now, and we'll have that in the Tulsa facility pretty soon. But we'll have one of Flavio's students will be coming over on a J1 to be working on that and setting that up this summer.
Awesome. So see you guys June 1st.
Awesome.
Fantastic. Great. Thanks. We look forward to that. With that, I know we've gone over, and I want to be cognizant of everyone's time, particularly for the academic folks here. It is that time of year where we have combination of exams, final projects, thesis defenses, and the like, all culminating in one perfect storm. So I don't want to quell the discussion, so we're happy to remain on for those that want to have further discussion. We will be doing some follow-up, particularly I noticed we'll probably have some meetings to talk about flight campaigns next week, in addition to the WindShape that we just mentioned with at AUVSI. So we might look for something immediately after the NCAR session, but I'll follow up with everyone in email and we'll find some good times. And then we'll look to have another follow-up meeting regarding some of the summer flight campaigns very soon. I know Adam will be very busy planning tourist campaigns, which will be coming up here shortly. So we'll try to work that around his schedule. Do we have any final comments or questions? Maybe from our NASA program managers?
Great to hear. No, I have nothing to add. Looks like good work. Thank you.
Great. Thank you all. Have a great Cinco de Mayo.
Thank you very much.
Thanks, Jamie.
Thanks, everyone. Great to hear everybody's progress. Very interesting.
I look forward to seeing all of you in AVSI for those that are going. For those that are not, I'll talk to you soon.
Sounds
Safe
good.
travels.
Bye.
Thanks, Jamie.
Nicholas J, could you hold on 5 minutes?
Great to see all the WindShape folks on board. This is Apurva signing off. Bye.
Thanks, Apurva.
Thank you, Apurva. Bye-bye.
Bye.